So, first of all, I'd like to express thanks to the organizers, and I want to say to Harold happy birthday. So, it's great honor for me to be part of the conference of celebrating the Harold's 80th birthday. So, I have been collaborating with Harold since my sabbatical in Vienna 8 years ago. So I'm grateful to you. As a hospitality and exciting new collaboration and so cherish memories for with my family and with your family. So anyway, so 80th birthday is special also in Japan. So I prepare some quiz for you. So in Japan, 80 years old is called Sanju. That means happy umbrella age. Yes, that's right. So the quiz is why is it called the age of umbrella? So, so nobody knows that. Ah, yeah, near. There is a hint in Japanese. So we describe the 80 by 8. So what do you think? Yeah, you you notice? Yeah, that is next hint. The umbrella is described by this. So this is the paint of this such kind of situation. The umbrella and the people. So yes, that's right. You know, this is 8 and this is 10. So it includes 80. So we call it umbrella age. So 80. Yeah. Yeah. So, uh, so we in Japan, so umbrella is some kind of symbol of kindness because it protect people from rain. So Harold is always kind, like umbrella. So, for example, when I try to communicate something, uh, so in that case, he always patiently listen to me. So even though I cannot speak English well and I cannot speak German, so thanks to your kindness, we our collaboration always succeed. So today's work is also based on the joint work with Harold and Naoyuki Kanomata is postdoc in my university and Raima. So I'd like to talk about the relationship between the Grosse-Wulkenhaar model and the n-body harmonic oscillator. Grosse-Wulkenhaar model is some kind of uh, matrix model. I will explain later. And Target model is already explained by the graph. So anyways, this talk is very easy to understand. Only elementary mathematics used. It's almost the first degree mathematics in university. So it's okay. So maybe I can I can make my talk be more shorter. This is my talk plan today. At first, I want to make briefs, a historical review, and next I like to explain the matrix model that is derived from the non-commutative quantum field theory. But maybe more of you are expert of this area, so maybe I guess it's. But the main part is section 3. I derived the five force kind of five force model is called uh, we we derive the harmonic oscillator system or Cardio model from this math. And I also make comments about the Grosse algebra and summarize. Okay. This is brief historical review. In 90s, matrix model was studied with the motivation from the two-dimensional duality or some non. So there is so many guys make great progress for the matrix models. So the most closest model is proposed by Concevich to solve the Witten conjecture. Concevich model is described by using this action. Lambda is a diagonal matrix. So the eigenvalue is meters, and there is a cubic interaction. And phi is a Hermitian matrix. J phi means some external. Sorry, I'm sorry. Removed. And so if we replace by this cubic model to 5 force interaction term, then the model is changed to our model, today's model. And in 2000, there is some other motivation comes from the non-commutative field theory. So especially the Grosse and Steinhackers and Grosse and Wulkenhaar shows that some kind of pi cubic model that is basically equivalent to the constant model and pi model are renormalized. So next, let's see why the matrix model comes from the quantitative. So for the simplicity, we use the simplest case, the Moyer plane. Here is a table of the coordinates. So if we use the complex coordinate set for x1 plus ix2 and its complex coordinate, commutator is equivalent to this. So of course, that means Moyer plane is non-commutative algebra of the continuous function. So it means if we choose some representation for the algebra, then everything is expressed by using matrix. This is the origin of the matrix. For example, we introduce some creation operator and another operator like that. So then the uh, commutator is written by this very famous Heisenberg. In addition, the differential operator is also written by those commutators. So that is the reason why, no, no, no. And let's introduce as an example of the representation. Let's introduce a Fock space. As you know, the vacuum state is defined by using the function state operator, and Kn is defined by using the operator. So if we introduce a number operator n, and this Kn is eigenstate, and we introduce a dual space, dual base by line, and that means this dual pairing orthonormal condition. Then using this representation, the scalar field is obtained by using the Hermitian matrix. And as quantum mechanics, the integration is replaced by trace operation. Okay? So the kinetic term of the scalar field is given by and use complex use. So it's as already mentioned, the derivative is replaced by using the commutator. So that is given by using the number operator and some another term written by using A. So removing this term by some potential or counter Lagrangian. So then we pretend you were mixing, so it's so they show that the model is normalizable. So removing this term is the point of here. This is an example of the phi cubic case. So phi is n by n Hermitian matrix, and n is the size of the matrix, and the E is a diagonal matrix. Mu is some mass. I is not the unit of imaginary number. I is eigenvalue of the number operator. And A is also some constant. So the partial function with external field is written by this guy. Measure is usual R measure. So that is invariant and UN transformation. Yes? Yeah, yeah. That is for denormalization. This term is always occurs. So, oh, yeah, yeah. So, yeah, yeah, yeah. If you don't like this, you can remove it. Okay. So using some free energy is a generating function with the endpoint function. There is some statistical number, and this is external field. So like slight complex. But anyway, that means connected green function. So I don't want to talk about this G detail, but G is described by using the Feynman graph on the Riemann surface like this. So this P11, P12, blah, 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 P1 means the external line comes from one boundary, and this P2 and P2 means the external line from the boundary 2, and blah, 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 and PB is the similar. So anyway, such complex endpoint function can be, we can obtain exact this endpoint function. So in this sense, the model is solvable. So indeed, we obtain this, all of them for large limiting field or CSP. And for finite and last year, we get some formula for. And 5/4 case is also solvable, and that is obtained by. And these guys are related with some topological recursion. Not familiar for. So anyway, now the time to get into the main scenes of my talk. So I'd like to explain from the 5/4 Grosse-Wulkenhaar model. From Grosse-Wulkenhaar model, I want to derive the harmonic oscillator system. So very easy. Calculation and proof is very easy. Action is here. N is the size of matrices, and E is diagonal positive. Eigenstate is positive. I'm sorry, eigenvalue is positive. And eta is just positive real number. And here is a 5/4 interaction. The patch, yes, the partition function is given by this guy. So the measure is visual measure. So the main theorem is given by this. So we define the function psi by the partition function multiplied by van der Waals determinant and the Gaussian factor. Then the psi satisfies the Schrödinger equation with zero energy. And this Hamiltonian is a harmonic oscillator Hamiltonian. This is the main result. Anybody harmonic oscillator? Okay. No, this is zero energy. I will explain what happened. Of course, everybody knows that there is no solution for zero energy. Maybe you ask about it. Sorry. we cannot, yeah, we cannot take eta zero limit. Okay. Anyway, let's see the proof. I explain what happened later, but anyway, let's see the proof. That is very simple. Is diagonal, but for diagonal E, we cannot derive the differential equation. So we change the variable to some non-diagonal H. So S is replaced by this guy. So it's different from the first one, but the partition function is the same because the measure has invariance under the UN transformation. So that is the same one, this guy. So the Schwinger-Dyson equation, the simplest Schwinger-Dyson equation is given by here, or almost Stokes theorem. So if this differential operator acts on this phi ij, then it's called the partition function. And if we this operator act on this kinetic term, then it's called is 2-point function. But now we bracket O is defined by this. This is not normalized by partition function, but anyway, maybe you can phi ij act this action, then it's so yeah, external, just constant. That's a parameter. And if we act this differential operator to the phi force term, then it's called the 4-point function. Okay. So next, let's consider the differentiator by Hij of this set. Then H is only here, so it's called it's differentiate from differentiator of this term, so it's called the 2-point function. And of course, if we consider the second order derivative by then it's called 4-point function. So we can abstract these terms to these guys. The Schwinger-Dyson equation is written by using this differential. Okay. Next, we return to the original variable EI. So this Laplacian is represented by using the EI, this differential operator. And this term is also like this. Of course, there is some other term, but the partition function depends on only the eigenvalue. So we can ignore the other terms. So then we get the differential equation for Schwinger-Dyson equation in this form. So we call it LSE. LSE looks sounds like something, but not so that. Just the Schwinger-Dyson equation like a Laplacian. Anyway, this is the differential equation for partition function. Okay. Then we consider the diagonalization of this operator, differential operator. It's easy to get it direct calculation by this. So then this operator is diagonalized by this Hamiltonian, and the Hamiltonian given by harmonic oscillator, n-body harmonic oscillator. So this is some kind of gauge transformation. So we introduce some cancelled transformation by this guy. Then psi satisfies the differential equation. This is a proof. Okay. So we can obtain more concrete expression for the partition function by using Ejections by integral. The result is given by this guy. So of course, the psi is also written by the similar expression. And using the Broggien's formula, so that is expressed by using some affine of Mij. Mij is defined by right? Anyway, so the question is what happened? So of course, Hamiltonian is positive. So in L2 function, there is no solution without zero. So it's yeah, it's natural question, I think. For example, n equal 1 case is very easy to understand. So harmonic oscillator system is for n equal 1 is sometimes called Weber equation. That is given by this equation. So now U is variable changing after variable changing of E. So U is given by this. So in that case, the psi is over here is easy to obtain by this guy. So if we use the modified Bessel function of second kind, then the psi is written this guy. So of course U is positive in this. So this is a function, but if you extend to the negative region, for this expression, we can define this psi u, but the behavior of this psi, it's this picture. So that means it psi doesn't. So this is the reason. But for any bigger than 1 case, the nature of psi is still unknown. So maybe Haroldo reveal this nature. Hope. Anyway, so far, I explained that how to derive the harmonic oscillator system from the five-force matrix model. So it is natural to wonder what's happen if we replace the Hermitian matrix to the real symmetric matrix. So this is the result. If we replace the phi Hermitian matrix to real symmetric matrix, then we obtain the Grosse-Wulkenhaar system. So only the difference is given by some kind of there is something different, half or one half. But anyway, the discussion is completely parallel. So the difference is given by this term. So Professor Olaf already that is the Carl-Zero system. Right, different point is there is some additional potential. That is not free capacity located in the some of the state, but there is some. So I'd like to make some comment about the Virasoro algebra. So for simplicity, at first we consider the Hermitian matrix model case. That is Hamiltonian is just a harmonic oscillator case. So if we change the variables like this, and the Hamiltonian is written by this guy. So using this creation and annihilation operator, this Hamiltonian is described by using the right. So if we introduce the Virasoro generator by this guy, then it satisfies the Virasoro or width algebra. There is no central charge. Yes. Sorry. Index. Ah, yeah. Yeah. Mm-hmm. Mm-hmm. Yes. Thank you. With, yeah. With algebra. Okay. So, in addition, the Hamiltonian is if only the constant term, so Hamiltonian satisfies such commutation relation. And the algebra doesn't change by the gauge transformation. So that means L-Schwinger-Dyson operator also satisfies this equation. We obtain the infinite number of differential equation for the partition. So for the Carl-Zero case, it's slightly complex, but Olaf already explains that how to do that. But anyway, we learn a little bit. So there is some additional term to the harmonic oscillation. So the point is using the Dunkel operator that is given by this guy. So this Kij is written in Sij in graphs, right? The same one. So that is called permutation operator. So it y coordinate yj change to yi. So if we write the operator equation, then we have to sorry. Yes, yes, that's right. Our model is completely determined. So only beta equals 1/2 case. Yes. So the commutator is also given by some extra. So using the commutator. Anyway, uh, with the algebra is once again by using this equation and operator using data, and this is not Hamiltonian, but if we introduce the h by this operator, then the h is written by this guy. But if we restrict our h to Kij invariant space, then the larger Hamiltonian is written by using some a transformation by the Undermont determinant, and or the Elshing-Dyson is the gauge transformation of the Elshing-Dyson is given by restriction of H. But please note that the partition function is invariant under the Kij. Ocean and so on is also invariant. So we can ignore this restriction. So we can use the H equal this guy. So the following can be discussed in the same way as in the case of harmonic oscillator. So we again obtain these differential equation, series of differential. So this is summary. So Schrödinger equation for the zero energy this, and the Hamiltonian of the harmonic oscillator or Cardier model. Cardier model is it marked is different from the the solution psi is given by using the partition function, and there is some from the partition function, and of course harmonic oscillator or Cardier model is a solvable model that has the expression of the width algebra. So we obtain using the algebra the partition function is of the. So thank you very much for your kind attention and happy birthday. So by the way, in Japan, the next grand celebration after 80s at the age of 88. The age of 88 is called Beiju in Japan, which means the age of rice. Rice. So this is Chris. Hi, the 88 is rice age. So I'll give you the answer in 8 years. So let's make the next conference in 8 years. Okay, thank you very much.